Infinity Labs, an open education initiative. Solid principles.
As software applications become increasingly complex, adhering to these principles is essential for producing maintainable and scalable code. In this series, we will provide a clear and concise explanation of each principle, along with real-world examples that illustrate its practical application. Whether you are a seasoned developer or just starting out, these videos will help you understand how to apply the solid principles to your code, resulting in higher quality and more reliable software applications. Join us for this informative and engaging series, and take your software development skills to the next level. The solid principles are a set of guidelines for designing software applications that assist in producing code that is of excellent quality, well-structured, and easily maintainable. In today's fast-paced software development industry, understanding the added value of using solid principles is crucial for building high-quality, maintainable, and scalable applications. The benefits of using solid are: high quality. The solid principles encourage the development of high-quality software that is robust, reliable, and easy to modify. Scalability. By promoting modular design, solid principles make it easier to scale the software as it grows. Maintainability. Solid principles improve code maintainability by making it easier to understand, modify, and extend. Testability. Solid principles help in creating software that is more testable, enabling developers to write automated tests and ensure that the code functions correctly. Code reusability. Solid principles promote code reuse by encouraging the development of modular and cohesive code that can be easily repurposed. The term SOLID is an acronym that stands for a set of 5 fundamental software design principles that provide a framework for building high-quality and maintainable software applications. Each principle addresses a specific aspect of software design and helps developers create code that is easy to understand, modify, and extend. The SOLID principles are as follows. The single responsibility principle is a solid principle that states that a class should have only one reason to change. In other words, a class should be responsible for only one task or behavior. For example, a user class should be responsible for managing user-related functionality such as user registration, authentication, and profile management. It should not be responsible for handling other unrelated tasks such as sending emails or generating reports. By adhering to SRP, classes become more cohesive and easier to understand, test, and maintain. The open-closed principle is a solid principle that states that software entities should be open for extension but closed for modification. This means that the behavior of a software component should be easily extended without requiring changes to its existing source code. An example of applying OCP is using a strategy pattern to allow for different sorting algorithms to be used interchangeably without changing the code that uses the sorting algorithm. With the strategy pattern, a new sorting algorithm can be added as a new class that implements the sorting interface, and the client code can use it without modifying its source code. This approach allows for the addition of new functionality without impacting existing code, resulting in more maintainable and extensible software. The Liskov Substitution principle is a solid principle that states that subtypes should be substitutable for their base types. In other words, if we have a class hierarchy with a base class and a derived class, we should be able to use objects of the derived class wherever objects of the base class are expected, without affecting the correctness of the program. For example, if we have a bird class and a penguin class derived from it, and the bird class has a method fly, the penguin class should either implement the fly method appropriately or throw an exception indicating that it cannot fly. By adhering to LSP, we can ensure that derived classes do not break the behavior of the base class and that the code remains robust and maintainable. The interface segregation principle is a solid principle that states that clients should not be forced to depend on interfaces they do not use. In other words, interfaces should be designed with the specific needs of the client in mind, and clients should not be forced to implement methods that they do not need. For example, let's say we have an order class that needs to interact with a payment interface. Rather than having a single payment interface that includes methods for all types of payments, such as credit card, PayPal, and wire transfer, we can split it into smaller, more focused interfaces such as credit card payment, PayPal payment, and wire transfer payment. This allows clients to implement only the interfaces they need, resulting in more modular and maintainable code. By adhering to ISP, we can create interfaces that are specific to the needs of the client, resulting in cleaner and more efficient code. The dependency inversion principle is a solid principle that states that high-level modules should not depend on low-level modules, but both should depend on abstractions. It also states that abstractions should not depend on details, but details should depend on abstractions. In other words, this principle suggests that we should rely on abstractions rather than concrete implementations to reduce coupling and increase flexibility. An example of applying DIP is using an interface to decouple the client from the implementation of a specific service. For instance, instead of a client class directly depending on a concrete email service class to send emails, it could depend on an email sender interface that defines the contract for sending emails. This allows the client to be flexible in its choice of email service, and it can switch to another implementation that implements the email sender interface without changing the client's source code. By adhering to DIP, we can create loosely coupled software components that are easy to maintain, extend, and test. In the upcoming videos, we will provide an in-depth explanation of each principle, along with practical examples to help you understand how to apply them in your own software development projects.